Welcome to the lesson Pre-Ignition Problems in Hydrogen Internal Combustion Engines and Their Solutions. In this lesson, we will explain how hydrogen engines need much more air than gasoline engines to burn efficiently, and how engineers balance the air-to-fuel ratio to optimize power, efficiency, and emissions. Let us look at our lesson objectives. By the end of this lesson, you will be able to define what pre-ignition is. Then, you will be able to explain why it is a major issue in hydrogen internal combustion engines. Later, you will be able to identify the common causes of pre-ignition and backfire in hydrogen engines. Next, you will be able to describe how different fuel delivery methods reduce or increase the chances of pre-ignition. Following that, you will be able to compare the fuel delivery systems in terms of benefits and risks. Next, you will be able to explain thermal dilution methods, including exhaust gas, recirculation, and water injection. Finally, you will be able to describe how engine design changes can reduce pre-ignition problems. Pre-ignition is the main challenge in hydrogen internal combustion engines. So, let's look at what pre-ignition is. Pre-ignition happens when the hydrogen-air mixture burns before the spark plug fires. When this occurs, the engine runs roughly and loses efficiency. In some cases, the flame can move backward into the intake pathway, which creates a backfire. Hydrogen engines experience pre-ignition more frequently than gasoline engines because hydrogen requires very little energy to ignite, burns over a much wider mixture range, and has a very small quenching distance, allowing the flame to travel close to metal surfaces before extinguishing. Now we will look at some of the major causes of pre-ignition. Research indicates that pre-ignition often begins in hot areas within the combustion chamber. Components such as spark plug tips, exhaust valves, or carbon deposits can remain hot enough to ignite the mixture prematurely. Studies also show that backfire can occur when the intake and exhaust valves overlap during valve timing, allowing the flame to move into the intake system. Oil can also contribute to the problem. Pyrolysis of oil is the high-temperature, oxygen-free decomposition of materials such as plastics or biomass to produce pyrolysis oil, a complex mixture of hydrocarbons that can be used as a fuel or chemical feedstock. However, this pyrolysis oil is often acidic and unstable, requiring further upgrading through processes like hydrogenation to become a viable, high-quality fuel. This presents a challenge that can involve high initial investment and technical complexity. Heat inside the chamber can break down oil that is present above the piston rings or inside small crevices. These oil vapors can enter the combustion chamber through blow-by, leaking valve seals, or the crankcase ventilation system, and then ignite early. What is a fuel delivery system? A fuel delivery system is a part of the engine that supplies hydrogen fuel to the combustion chamber. It controls where, when, and how much fuel enters the internal combustion engine. The design of the fuel delivery system affects engine performance, safety, and the chance of pre-ignition. In hydrogen engines, fuel delivery is especially important because hydrogen ignites very easily, and controlling fuel placement helps prevent unwanted ignition. Fuel delivery systems are one of the primary methods for reducing pre-ignition, as fuel can be introduced at various points in the intake or combustion process. This adjustment alters the temperature and amount of hydrogen stored in the intake system, leading to safer operation. Fuel delivery plays a major role in controlling pre-ignition in hydrogen engines. There are three main methods of fuel delivery: central injection, port injection, and direct injection. We will look at each of these methods as we proceed through this lesson. Let's look at the first main method of fuel delivery system: central injection or carburetted systems. These systems are simple and effective methods that operate at lower fuel pressures. They are commonly used in gasoline engines, which makes conversions easier. However, they have the highest risk of pre-ignition because a large amount of hydrogen-air mixture sits in the intake manifold. If ignition occurs backward, the manifold mixture can ignite and create a strong backfire. Now, we will look at the second main method of fuel delivery system, the port injection systems. Port injection helps reduce pre-ignition because hydrogen is injected directly into each intake port rather than a single central point. By injecting the fuel after the intake stroke has started, the temperature inside the chamber is lower, reducing the likelihood of pre-ignition caused by hotspots. Port injection also stores a much smaller amount of hydrogen-air mixture inside the intake manifold at any given time, which means that if a backfire occurs, it is less severe. Port injection systems use two common control methods. The first is the constant volume injection (CVI) system, which uses a mechanical camera-operated device to control the timing of hydrogen delivery to each cylinder. The second is the electronic fuel injection (EFI) system, which uses electronic injectors on a fuel rail to control how much hydrogen is sent to each cylinder. EFI controls fuel timing electronically, while CVI controls timing mechanically. Now, let's look at the third main method of fuel delivery system: direct injection. Direct injection offers the greatest control. In this method, hydrogen enters the cylinder only after the intake valve closes. As a result, the mixture inside the intake system cannot ignite, and backfire into the intake manifold is eliminated. Direct injection also increases power output compared to gasoline and carbureted hydrogen engines. However, this method requires higher fuel pressure and does not completely remove premature ignition inside the combustion chamber. Because there is less time for the air and fuel to mix, the mixture can be uneven, which can lead to higher emissions of oxides of nitrogen. Let's look at this table to compare the three methods of fuel delivery. Central injection, also known as a carbureted system, is the simplest method for supplying hydrogen to an engine. It does not require high fuel pressure, and it is easy to convert from a gasoline engine, making it both inexpensive and practical. However, it has the highest risk of pre-ignition and backfire because a large amount of hydrogen-air mixture collects in the intake manifold. When pre-ignition occurs, the stored mixture can ignite and cause severe backfire, making this delivery method less safe and less stable than other systems. Port injection provides better control. In this method, hydrogen is injected directly at each intake port and delivered after the intake stroke has begun. This means the temperature is lower during injection, which reduces hot spots and lowers the chance of pre-ignition. Only a small amount of hydrogen-air mixture is present in the intake manifold at any given time, so if backfire occurs, it is less severe. Port injection does require higher fuel pressure than central injection and is more complex, but it is safer and more reliable. Direct injection is the most advanced system. It delivers hydrogen directly into the cylinder after the intake valve has closed. Because the intake system does not contain a hydrogen-air mixture, backfire into the intake manifold is fully eliminated. Direct injection also increases power output compared to gasoline engines and carbureted hydrogen systems. However, it does not completely remove the possibility of pre-ignition inside the combustion chamber. There is also less time for air and fuel to mix, which can result in uneven mixtures and higher emissions of oxides of nitrogen. Direct injection needs high fuel pressure and more sophisticated components. What is thermal dilution? Thermal dilution is a method used to lower the temperature inside the combustion chamber by adding cooler substances, such as exhaust gas or water, thereby reducing the chance of pre-ignition and lowering emissions. Thermal dilution reduces combustion temperatures and helps prevent premature ignition. The common methods for thermal dilution systems are exhaust gas recirculation, abbreviated as EGR, and water injection. Let's look at the first method of thermal dilution systems: exhaust gas recirculation. EGR sends part of the exhaust gas back into the intake. This lowers hot spots in the combustion chamber and reduces nitrogen oxide emissions. Usually, recirculating 25 to 30% of the exhaust gas is effective. The downside is a slight reduction in power as less fresh air enters the cylinder. Let's look at the second method of thermal dilution systems: water injection. Injecting water into the hydrogen stream before it mixes with air cools the incoming fuel and lowers the chance of premature ignition. This method is more effective than injecting water directly into the hydrogen-air mixture in the intake manifold. A potential issue is that water can leak past seals and enter the engine oil, thereby reducing lubrication and increasing wear. Engine design changes are one of the most effective ways to control premature ignition. A disc-shaped combustion chamber with a flat piston and chamber top reduces turbulence and swirl that can trap heat. Hydrogen engines can also utilize a larger bore-to-stroke ratio as they do not produce unburned hydrocarbons. Two spark plugs help ensure complete combustion over a wider range of air-fuel mixtures. The cooling system must distribute coolant evenly throughout all areas that become hot, ensuring that no location becomes a hot spot. Using two small exhaust valves instead of one large valve keeps temperatures lower at the valve surfaces. A good scavenging system is one that removes the exhaust gases left in the combustion chamber and replaces them with fresh air. When the chamber is cleared of exhaust gas, it reduces trapped heat and lowers the chance of pre-ignition. Let's look at the summary for our lesson on the pre-ignition problems in hydrogen internal combustion engines and their solutions. Pre-ignition is a primary issue in hydrogen internal combustion engines. It happens when the hydrogen-air mixture burns before the spark plug fires. When this occurs, the engine becomes rough, loses efficiency, and the flame can move backward into the intake system, causing a backfire. There are several causes of pre-ignition. Hot areas inside the combustion chamber, such as spark plug tips, exhaust valves, and carbon deposits, can cause the mixture to ignite prematurely. Oil vapors can also enter the combustion chamber through blow-by or valve seals, and these vapors can ignite before the spark plug fires. Fuel delivery systems play an important role in preventing pre-ignition. Central injection is simple but has the highest risk of backfire. Port injection reduces this risk by injecting fuel at each intake port. Direct injection delivers the fuel after the intake valve closes, which eliminates backfire in the intake manifold. Thermal dilution is another method used to prevent pre-ignition. Exhaust gas recirculation sends part of the exhaust gas back into the intake, cooling hot spots. Water injection cools the incoming hydrogen. Both methods lower the temperature and reduce the chance of pre-ignition. Finally, engine design changes can help control pre-ignition. A disc-shaped combustion chamber reduces heat buildup. 2 spark plugs help ensure complete combustion. An improved cooling system prevents hot spots. 2 small exhaust valves stay cooler than 1 large valve. A good scavenging system removes leftover exhaust gas and replaces it with fresh air, reducing heat inside the chamber. Thank you.